Our last reaction in this chapter is a base-promoted halogenation reaction that is often known as the haloform reaction. In this reaction, we're going to start with either a methyl ketone, which is a ketone in which one of the carbon groups is a methyl, or a 2-alcohol. In other words, an alcohol where we have a methyl on carbon 1 and the OH is attached to carbon 2. We're going to use excess halogen. We're also going to use excess sodium hydroxide. In this reaction, the sodium hydroxide is not a catalyst. So that's why it's not base catalyzed. Instead, the hydroxide is consumed. However, it makes the reaction go much faster. So we call reactions like that promoted reactions. The product of this reaction will be a deprotonated form of a carboxylic acid using the C double bond O and the non-methyl carbon group of the original ketone, and a molecule that looks like this, a carbon that has 3 halogens attached and a hydrogen. So it has the formula CHX3. These molecules have the common name haloform. For example, if there's a bromine as the halogen, it would be called bromoform. The mechanism of this reaction looks like this. The initial methyl ketone is deprotonated on the methyl side. This would be the kinetic deprotonation. It would make the kinetic enolate. Now, although we are using a relatively weaker base than LDA, we're making this enolate in the presence of the halogen. So therefore, as soon as it is formed, it can react with the halogen and therefore become not an enolate anymore. That prevents it from equilibrating to the thermodynamic enolate. So the result of this would be to put one halogen on the alpha carbon in place of a hydrogen. However, there are still 2 other alpha hydrogens. We're using an excess of base, so we can repeat this process 2 more times, one for each additional hydrogen, until all of the alpha hydrogens are replaced with our halogen. That would create a molecule that looks like this. The base then can do a nucleophile attack onto the carbonyl carbon, pushing a pair of electrons out of the way and creating an intermediate that looks like this. That intermediate is a tetrahedral intermediate. It's unstable. It has electron pressure pushing back down toward this central carbon. And it turns out that the CX3, the carbon with 3 halogens on it, can act like a leaving group because they pull electrons away from the central carbon. So they stabilize the minus charge that would be formed on that carbon. This is an inductive effect. Therefore, the tetrahedral intermediate pushes down with electron pressure, pushes out the CX3 as a CX3 minus, and then the CX3 minus rapidly deprotonates the carboxylic acid that would have been formed, transferring a hydrogen from the carboxylic acid to the CX3 minus, making our haloform byproduct and making a deprotonated carboxylate. This reaction also works for 2 alcohols, which are not ketones and can't do the deprotonation initially. However, it turns out that sodium hydroxide and halogen can oxidize the secondary alcohol to a ketone, which is now a methyl ketone. It then goes on to do the haloform reaction and give the same products. When iodine is used as the halogen, we can perform a chemical test that is called the iodoform test. This is a classical chemical test for methyl ketones and 2 alcohols. It's been useful to be able to test for methyl ketones because they appear in a lot of important biologically active molecules. In this test, we take the methyl ketone, we treat it with our haloform reaction conditions, so iodine plus hydroxide. At the end of the reaction, we get a carboxylate ion and we get iodoform. This reaction is run in water, aqueous solvent. It turns out that iodoform is not water soluble and it forms a yellow solid precipitate. So we can use this as a chemical test because if we take our unknown molecule and we mix it with the haloform reagents and we get a yellow precipitate, we can conclude that our unknown molecule was either a methyl ketone or a 2 alcohol.